Okay, good morning, everybody. So I'm going to actually start. The main theme of today's lecture is going to kind of hook up with some of the stuff that Melanie is going to talk about. I'm going to talk about what the Cohen-Lenstra heuristics look like from this point of view, but I think maybe I'll actually start for the first few minutes by just giving a kind of whirlwind tour of some of the things that I am not talking about in this lecture series, just to kind of give some sense of the scope of like what kinds of things people are thinking about. So let's sort of say geometric, analytic, number theory, that will not appear. And so I just want to say, give a sort of brief list of things that when I talk about it and talk in each case about at least what variety is the variety whose geometry we might be studying in order to address this problem. So for instance, we could talk about geometric twin primes, or more generally, prime clusters. And here, the variety would be sort of similar to the one that we discussed for Chowla. I mean, it might look something like this. So the moduli space of what you might call factored F and factored G, such that G equals F plus 1. More formally, I could say it's the moduli space of two n tuples. So this is just A to n so far, but I'm going to put a condition. I'm going to cut down a rather high codimension subvariety of this space, such that if I look at the polynomial with roots x minus z1, x minus zn, then that differs by 1 from the polynomial with roots w1 through wn. So somehow this variety is not just a variety, it's a variety with an action of Sn cross Sn, right? Because you can permute the z's or you can permute the w's, and it doesn't change this condition you're putting on. So this carries an action of Sn cross Sn, and understanding the cohomology of this variety with its Sn cross Sn action would carry lots of information about essentially how the factorization of F relates to the factorization of F plus 1. So, and I think, by the way, similarly, I don't know what the cohomology of this variety is, but one can certainly figure out things about the H0, and so as a result, you will see that there is stuff in the large Q limit about precisely these problems. So I'll just put up a couple of names. Paul Pollack, who I think, you guys know Paul Pollack has an A in his name, right? Not an O, right there where I'm pointing. Good, okay. And also Lior Barry Soroker, you can go see, and they have both in fairly recent papers have proved the sort of large Q limit versions of these theorems, essentially when you unpack it, precisely by proving that this variety is irreducible, so by controlling the H0. Okay, so that's one. Melanie mentioned the conjectures, first the conjecture of Mala and then the more refined conjecture of Bhargava about number of number fields of bounded discriminant. Maybe I'll even put Linux name in here too, because I think he's kind of said to be the first guy who conjectured that the number of degree n number fields of discriminant x was asymptotic to some constant times x. And in this case, right, where we're counting degree d extensions of Q, or more generally, extensions of Q with Galois group G, I endorse Melanie's abusive notation when we talk about the Galois groups of non-Galois covers. Then the relevant moduli space is something like xn equals moduli space of degree d covers, or if we're specifying the Galois group, G covers of the projective line. With n branch points. And these moduli spaces are ones that are certainly already studied in algebraic geometry. They're called Hurwitz spaces. So again, sort of proving stable cohomology theorems for these kinds of varieties would be, in some sense, the geometric version or a geometric version of these Linnik-Malapakova conjectures. Bjorn mentioned the conjectures of himself and Eric Rains about the distribution of the mod p Selmer groups of elliptic curves varying in a family. So one way to think of, if you were to sort of ask yourself what the geometric manifestation of that conjecture would be, it might be something like, I mean, we would have to replace our elliptic curve over Q by an elliptic curve over FQ parentheses T and study the mod P Selmer group of that. How do we understand this thing? Well, an elliptic curve over FQ parentheses T, we could think of as an elliptic surface over FQ. So I'm going to be quite vague about, this is something that we discussed a lot at the AIM conference that Chantal and I and Alina too organized at AIM a couple of months ago. So I think there's a way to express this in terms of a certain moduli space of elliptic surfaces together with let's say elements of H2 of the elliptic surface with Z mod PZ coefficient. So what happens is the Selmer group of an elliptic curve over a curve turns out to be related by spectral sequence to the H2 of the elliptic surface considered as a surface, the middle cohomology. And by the way, to connect this with what Chantal was talking about, the H2 of a surface has a product pairing, just like the H1 of a curve, but the sign of that pairing depends on the parity of the degree of cohomology. So H1 of a curve, as you guys know, carries a symplectic pairing, the Weil pairing. H2 of a surface carries a symmetric pairing, an orthogonal pairing, and this is in some philosophical sense why, when we study these things having to do with the L functions of elliptic curves, you see in Chantal's stuff that is related to orthogonal matrices, whereas when we study something like class groups, which are more like the H1 of a curve, that's the example I'll talk about mostly today, that's more like symplectic. So I mean, this is one way of seeing like why one is a symplectic family and one is an orthogonal family. So maybe I'll just draw a little line here. I'm going to mark that there's an orthogonal pairing here. I have even more on this list. I'm going to say almost nothing about this. Linnik-Duke is a theorem about equidistribution of Heegner points. And there's a very beautiful recent paper, which I highly recommend, by Vivek Shenda and Jacob Zimmerman, who show that when you ask this question over a function field, you can actually prove the analog again by the exact same method, by computing the stable cohomology of some families of varieties, and in this case the variety are generalized theta divisors inside abelian varieties. And finally, maybe I'll just mention something I like a lot, geometric Potirov-Manin. So I mentioned at the very beginning that a sort of one of the most famous classes of problems in arithmetic statistics, which is not so much what we're talking about at this workshop, but you ask about rational points of bounded height on a variety and ask about the asymptotics of that. Well, the function field version of that would be take some variety and look at its points over FQ parentheses T. So loosely speaking, if X is some variety, its FQ parentheses T points, at least generically, are like maps from P1 to X. So maybe I'll say if X starts life as a variety over FQ, then its FQ parentheses T points are like sort of families of points on T, like a P1 on T. And so what we would study is something like this. And the height of such a point turns out to be the degree of this map. So the relevant moduli spaces would then be xn equals degree n maps from P1 to X. And one thing that's nice about this is that this makes contact with a subject that's of great interest in algebraic geometry and topology, which is spaces of rational curves on varieties. So I mean, you fix some variety, even over the complex numbers, and say I'm going to look at the space of rational curves of higher and higher degree, and ask whether those spaces, which get higher and higher dimensional, actually have some kind of limiting behavior. And in this case, this is not a problem that we invent as number theorists and then go try to see if we can figure out anything about it. It's actually an existing school of thought within algebraic geometry that people already think about. And one thing that's cool is that if you go look at the literature in this area in algebraic geometry and algebraic topology, you find that the classes of varieties for which the relevant geometric facts are known match very well with the classes of varieties over Q for which the theory of Riemannian is already known. I mean, the arguments are totally different, but there's some kind of parallel play going on between those two fields. So, so this list, I mean, as you see, I'm not going to talk in depth about any of these things, but I just want to kind of argue that there really is sort of some scope to this general program. So I guess another sort of definition of what we mean when we sort of, what is the geometric and geometric analytic number theory is the word geometric is kind of an operator that you can prepend to the name of a famous number theorist and then refer to something that they would not recognize as have anything to do with their own work. So in that sense, it is the same as in geometric Langlands, right? So I actually made this point at a conference in honor of Langlands, and everybody laughed, except Langlands, who was like, yeah, that's a good point. So okay, but the actual math I want to talk about and not talk about philosophy today is what happens when we sort of investigate these Cohen-Lenstra conjectures that Melanie has been discussing in her talk. So for the rest of the talk, let's turn to that. And I want to, again, talk about what's known and also talk about the large Q limit and what this has to do with monodromy. So maybe I'll start with a new Sharpie. Okay, so let me get to the right point in my notes. So I think, again, in the interest of kind of keeping things simple, I'm not going to say this in the most general way that Melanie did. I think for the sake of this talk, I'm just going to talk about what Cohen-Lenstra says about the L torsion of a class group, not about the whole L primary part. So let me make I'm going to write down a conjecture, but I emphasize that this is like only a small part of what Cohen and Lenstra actually conjecture. So let B an odd prime and E sub R L capital N, lots of indices, be the expected value as D ranges over square-free integers in n comma 2n of the following thing, surjections from the class group of Q adjoin root minus D. Okay, so this is the entity we're studying, right? We take a random number and adjoin its negative square root. So this is like a random quadratic imaginary field drawn from some box. And we're going to probe this thing by asking how many surjections it has onto Z mod LZ to the R. So this is what you might call a moment. I mean, if R is 1, we're asking about essentially the, we're almost asking about the average size of the L torsion in the class group. If I wrote HOM instead of surge, that really would be like the number of L torsion points. In fact, it's the number of L torsion points minus 1, because the only map to Z mod LZ that is not surjective is the 0 map. So we want to exclude that. It sounds like you can't read what's inside the surge. Okay, so here, I'm going to blow it up with a little magnifying glass. Oh, they're covering up the, oh, you weren't talking about, now I understand. Is that the complaint, or you need me to write bigger what was? Okay. So this is the class group of Q adjoin root minus D, so whatever the mystery sort of random abelian group. And then how many surjections from this thing to, so I'm writing it smaller now, actually. I don't know if that's, if that's helpful. So e.g., so maybe I'll say this. So e.g., by E n L1 is the expected value of the size. I'm just going to write CL for the class group of the random field of the L torsion in the class group minus 1. And so the conjecture, I mean, I've sort of said a thing, but I haven't closed the conjecture boundary. Then we conjecture is that the limit, as n goes to infinity, we make the box larger and larger, exists and is equal to 1, which is kind of cool for all R. So one way to think of this is that it's really telling you what is the distribution on the dimension of the L torsion, because if you have like a mystery vector space over a finite field drawn from some distribution that you don't know, but you know on average how many surjections it has to Z mod L, how many surjections it has to Z mod L squared, how many surjections it has to Z mod L quantity cubed, et cetera, et cetera. It's kind of like having like a mystery random variable, and you know the expected value of it, of its square, of its cube, et cetera, et cetera, et cetera. Under favorable circumstances, you have to be like a bit careful in a way I'm not being in these talks. That's the same information as knowing what the probability distribution is. So you should think of this as kind of a rephrasing of the usual Cohen-Lenstra conjecture that you may be familiar with about what is the L rank, like what is the dimension of this Z mod L Z vector space. They actually conjecture a probability distribution for this, and this prediction is compatible with that. So this is the version of Cohen-Lenstra that that's most convenient for talking about things geometrically. So what's going on? So now I want to sort of walk through this same process that we did with counting square frees and with Chala to kind of see what it says. So yeah. If there's a P, it's the same as L. Where's there a P? Ah, yes. The only P is here, right? Usually we say P. I'm saying L because there's going to be a finite field FQ, and I don't want you guys to think that P has the same characteristic as Q. So that's why I'm writing L, to emphasize that it's a different characteristic. So, okay. And actually, I'm about to do that. So what is function field Cohen-Lenstra talking about? And now I'm sort of revisiting some of the things that Chantal said about what happens when you make this comparison between function fields and number fields. So function field Cohen-Lenstra. So we have, on the one hand, O, the ring of integers of Q adjoint root minus D. And if you'll recall, the way we deal with this on the function field side is, so taking O is like we've chosen, we have this prime at infinity, and we're looking at everything that's integral away from that prime. Of course, in the member field setting, there's no notion of integrality at the prime at infinity. But we are sort of imposing conditions at all primes but one. And in the same way, this kind of revisits what I said in the first lecture. The analog of that is U, the affine curve, which is, so I better say the curve first, right? So the field itself, you should think of as having something to do with a curve, y squared equals f of x. I think I said this before, that square-free integers correspond to square-free polynomials. But the actual thing we want to study is this affine curve. Maybe I'll call this C sub f, CF minus the point I'll call infinity. So what is that point? Remember, I chose an infinity in P1. We are going to have n be of odd degree. And again, we saw this in Chantal's talk, that you sort of have to be careful about the behavior at infinity. I'm always monic, so like Chantal, I don't have to worry about the inert case at infinity, and I'm making n odd, which means that my cover of this hyperelliptic curve of P1 is ramified at infinity, so there's just one point over infinity. And that's what we call quadratic imaginary, because quadratic imaginary field also has only one Archimedean place. So n odd is kind of like the imaginary case, so to speak. And we're going to take out that point and have an affine curve. Again, ideal in this ring of integers corresponds to, maybe I should say, an effective divisor on U, and principal goes with principal. And so when we study the class group, you might say that this is like the Picard group of U, but it turns out that because you have just this one point at infinity, this is identified with the Jacobian of the actual curve itself, or rather, it's FQ points. So I went through this a bit fast because I think like we've talked a lot in general about the analogy between number fields and function fields. So let me just say that it's in the notes, and I'll let you guys sort of piece through this together yourself. But the point is that given a square-free integer, there is a canonical way to get a nice natural abelian group, namely the class group of QJ and root D. Given a square-free polynomial, there's a very natural abelian group floating around. Namely, I generate a hyperelliptic curve by taking the square root of f, just as I took the square root of d, and then I look at the Jacobian of that curve, which is an algebraic variety over fq, an abelian variety of some large dimension, and then I look at its FQ rational points, and then again I get an abelian group. And it's a sort of long-standing piece of philosophy that these two things are supposed to sort of somehow be alike. And so in particular, if we want to study the L torsion in the class group of O, that should be like studying the L torsion of this Jacobian. So, so class group of O, the part killed by L, should go with the L torsion of the Jacobian. So this is some kind of, over the algebraic closure, this is some kind of Z mod LZ to the 2G, right? It's a 2G dimensional vector space over this field, but Frobenius acts on it, and we only want to look at that stuff that's FQ rational. So maybe at some point on this slide, I should always say that using different letters is not enough. I should definitely say that L is not equal to the characteristic of FQ for this discussion. So what we're on our way to, by the way, having drawn this whole chart, is I'm trying to get to the point of what is the variety whose points we're counting. When we make this assertion of Cohen-Leinster in the function field, the assertion is always supposed to be that we can express this claim as the counting of points of some variety, and that's what I'm on my way to defining, just to give a roadmap. Okay. And I've essentially already done that because now let me tell you what space we're going to make. Let's define so this suggests a definition so comp n, that's the thing we've seen before, but now I'm going to put comp n parentheses L. So this is supposed to be a configuration space with level structure. Those of you who have studied the moduli of elliptic curves sort of know very well that when I put, okay, so for the elliptic curve span, this would be a little bit more like conf n lower 1 of L, but that's too many indices, so I'm just going to call it conf n parentheses L. So is the moduli space of, let's say, hyperelliptic curves with L level structure, that's what we might call it in words. More formally, it's pairs F comma P, where F square free monic degree n. And actually now for this definition, we don't really care whether n is even or odd. That's sort of to make the analogy with class groups work, but actually everything I say from now on is going to be fine whether n is even or odd. So F is the kind of thing that's parameterized by comp n, but then P is an L torsion point in the Jacobian of this curve. So this is a cover of comp n. And maybe I'll say, yeah, let me say the way I've set this up. Non-zero. So you have a choice. I mean, it's just like when you say x1 of n, moduli, you don't say the moduli space of elliptic curves with an n torsion point. Usually you say with a non-zero n torsion point, right? So that's what I'm doing. I'm going to do that here too. And hopefully I've got this convention the same throughout all my notes. So comp NL maps to the comp n that we've been discussing through these whole talks. Namely, you just remember f and forget p. And this is a map. It's a finite map, right? Because its fibers over a given f are just the non-zero L torsion points. So this is a finite, in fact, a finite état map of degree L to the 2g minus 1, where g is the genus of the hyperelliptic curve, which you can determine from n. Okay. So now let's think about, and I claim this is the variety, or we'll see later, one of the varieties whose points we want to count. So now let me define, I have to make the function field definition to the thing I'm trying to count. So let's define E, are you ready for a lot of indices? EQLRN is the expected value, as f is chosen randomly from monic square frees of degree n, of the number of surjections from, well, the analog of the class group, which is this group, the FQ rational points in the Jacobian, and we're taking the surjections to Z mod LZ to the R. So it really is the same thing as before, but there's sort of like a lot of knobs that we can tweak. R is tweaking sort of which moment we're taking, N is tweaking, so to speak, the sides of the box, L is which prime we're doing Cohen-Lenstra for, and then Q is the finite field. Whew, okay. But for the moment, let's concentrate on R equals 1, because already a lot of the ideas are already there. And as Melanie said, even for R equals 1, right, even for the average size of the L part of the class group, we basically don't know anything except in case L equals 3. So we agree there's still some difficulty there that's worth discussing. So let's take R equals 1 for a minute. So what is, so EQL1N equals average of the size of the L torsion here, but then one of these rational points is 0, and we don't want that, so that's the average of this. But this can be expressed precisely in terms of this variety I have over on the other side of the page. So let me give this a name. I'm going to call this pi, this projection from comp NL down to comp n, and the set of non-zero torsion points, the set of non-zero L torsion points on this Jacobian is, by definition, the fiber of this map over F. Or more precisely, it's the rational points in the fiber of F over this map. So this is of the number of, so okay, I take pi inverse of F. So I take some square free polynomial, I look at its preimage under this map, and I get some stuff. I mean, I said it's a map of degree L to the 2g minus 1, so over the algebraic closure, I get L to the 2g minus 1 points, but they may be permuted by Frobenius every which way, and the things I'm trying to count are the fixed points for Frobenius acting on this space, like the ones which are actually defined over FQ. So this is the average of how many FQ points there are in the fiber, but then that average is just the number of points on this variety divided by the number of points on this variety. I mean, that's what it means to take the average number of points per fiber. So this is comp NL FQ over comp n FQ. And so what we see is that what Cohen-Lenstra is telling us is something that geometrically looks very handsome. It's saying that this quantity in the limit in n goes to 1. I like that, so I'm going to give it its own pride of place at the top of the next slide. So CL predicts that the limit as n goes to infinity of comp n of L FQ over comp n of Q equals 1. And by the way, you may say, oh, I immediately see. So, okay, who knows how to prove this? We don't know. But then you immediately see, if you sort of like the last talk, that you're like, aha, now I can like get out in front of the game and prove the large Q limit of Cohen-Lenstra, because I can use Weil to say that that bottom guy has about Q to the n points, and the top guy is another n-dimensional thing over FQ. So I'm going to hit it with a Weil hammer and say that all the contribution of higher cohomology goes away, and in the large Q limit, it also has about Q to the n points. And so that limit is 1. 2 comments on that. 1, somebody already did that. You won't be surprised to hear. And much more. So I mean, this is kind of step 0 of a beautiful paper of Jeff Actor, who I don't know if he's around this morning. He might be with his kids, but who uses sort of exactly this approach. I don't remember the exact year of the paper, within the last 10 years, to show a kind of large Q limit Cohen-Lenstra. But the other thing you should object to is that there's something I didn't do. So maybe I'll even write this down. So note, the limit as Q goes to infinity of this same quantity is Q to the n over Q to the n equals 1. But then I've got to do a big if. Remember with Chawla, I was like, oh, look, you just use Weil, and like it goes to Q to the n. But there is actually something you have to prove, right? You had to prove that that variety was geometrically irreducible. Like Weighing away everything except H0 doesn't leave you with nothing to do. It leaves you with H0 to understand. And again, if you're used to elliptic curves, like you never really think hard about the fact that x1 of n is connected, because probably you think of it as like the upper half plane, like mod some group, so of course it's connected. But in some sense, there is actually content there. So let me just say, if comp n of L is geometrically irreducible. And actually, since this is an étale cover of a smooth thing, it's the same to say, in this case, connected. So I'll probably use the language of connected components rather than irreducible components for the rest of this talk. So that has content. And this kind of leads me to what I wanted to sort of have to be the theme of the last part of this talk, with what kind of content is necessary to prove this irreducibility. These are going to be big monodromy theorems. And so this is the sort of the relevance of monodromy to Cohen-Lenstra type problems in the large Q limit. How to think of this? So think of comp NL to comp n. I mean, let's be geometric for a moment and just think of this over C. And now for today's lecture, I'm going to be completely, I'm not going to say so much about the comparison between complex numbers and FP. I'm just going to do topology, and you have to believe me that everything is going to be okay. We can translate over to the characteristic P side. So I mean, a covering space, now we're sort of back in algebraic topology 101, right? A covering space is given by an action of the fundamental group of the base on the fiber. So this is as an action of pi 1 of the base on the fiber. So maybe I should sort of specify some base point there. Maybe I'll call it F. On the fiber of this map on F, which is isomorphic to Z mod L Z to the 2G, this pi 1 we've already seen is the braid group on n strands, right? That's something we've already discussed. So the braid group is always going to be an actor in this setting. So you have the braid group acting on the set Z mod LZ to the 2G. But as is familiar from what you know about elliptic curves, and it's the same here, it's not just acting on it as a set. I mean, this Jacobian is a family of group varieties, and the addition is preserved by the action. So this is not just a permutation, it's a linear action. So it's a representation of the braid group. So already you see that you're sort of talking about stuff that topologists like studying representations of the braid group. And if you were to, it's kind of cool, if you were to do this instead of hyperelliptic curves, if you were to do like what Chantal did, instead of say like, let me think about y cubed equals f of x, y fourth equals f of x, et cetera, you would rediscover the so-called Burau representation of the braid group that the topologists like. These are sort of the specializations of that where the parameter goes to the root of unity. So this is like the specialization of Burau at q equals -1 for the braid group fans in the house. Anyway, it's a linear action, but it's even more than that because there is this Weil pairing on the L torsion points of a Jacobian, which is also preserved by everything. And it's an alternating pairing because it's on H1 of a curve. And so this is preserved too, which preserves a symplectic form, i.e. a map from braid group of n to SP2G Z mod LZ. I mean, of course, I'm doing something kind of gross by like choosing a basis, and it might be better if I kind of kept track of the base point for all time and it was like, oh, it's like a Weil pairing preserving linear automorphism of the Jacobian of this base point. But I'm going to kind of make everything concrete and do matrices, and just say this. So this map, this homomorphism, is what we call the monodromy homomorphism of this cover, and the image of the braid group in here is what we call the monodromy group. So let's now, from this point of view, why am I saying all this? Because if we have a covering map of spaces, and we want to know whether the top space is actually connected, this is equivalent to asking whether the action of the fundamental group is transitive on the fiber. Those are the same things. So to say conf n L is connected, which is what we need to know, is exactly the same as saying that that the braid group of n acts transitively. Oh, so I made a slight mistake. Sorry, the fiber is not quite this. It's this minus 0, right? Because the way I always have to make this choice of convention, and the choice I've chosen for this talk is to have it be parameterizing non-zero vectors. So it's actually these are the things on which it acts, and that's good because I'm about to claim that this group acts transitively on vectors, but if 0 is in there, it certainly doesn't act transitively because it always preserves 0. So acts transitively on non-zero vectors in Z mod LZ through the 2G. So one thing you can do is you can actually, it's not so hard to actually like write down what matrices the braid generators go to, and then you can like while away a pleasant rainy afternoon, like showing that it acts transitively on vectors if you want to. But let me tell you what we know that makes this true. So this is true because we know that this monodromy map is actually surjective. And so the question, I mean, to ask questions about the transitivity of this action, all we need to know is what's its image in the symplectic group. So this transforms it. Now suddenly the braid group is gone. And now we're asking a question about matrices. We're asking whether the symplectic group acts transitively on non-zero vectors. And it does. Um, so again, why do we know this? And this is precisely what I mean by a big monodromy result. If you remember, I sort of described this Chalo thing in a somewhat pretentious way by saying that it was kind of a big monodromy result where because the thing we were taking the square root of wasn't a perfect square, something surjected on Z mod 2Z, and that made the covering space irreducible. The exact same thing is happening here, but the surjectivity is somewhat harder. So this is, I think, this has been proved by various people at various times. There's a kind of topological version proved by Ocampo. There was a kind of version proved by Jukang Yu that was sort of a samizdat unpublished paper, like circulated around for a long time, but that didn't appear. And it was reproved by, actually the monodromy result, wait, that might be actor Priest. Does anybody here know whether the hyperelliptic one is? I think, yeah, I think it is, okay. Jeff wrote, I think the Cohen-Lentzer paper is just Jeff, but I think the monodromy paper is actor Priest. And also Chris Hall. So now there's lots of proofs in the literature. And then it's just a matter of linear algebra. And in fact, what's more, so in fact, this big monodromy result gives that the limit, that the large Q limit of the average of the number of projections from the Jacobian to Z mod LZ to the R equals 1 for all R. So I just told you about the case that R equals 1. For a higher R, you can make a moduli space which kind of keeps track of, instead of parameterizing a single L torsion point in the Jacobian, it parameterizes, maybe working dually from surjections, a subspace of dimension R of the Jacobian. And what it amounts to is, I'll just tell you, it amounts to, but now I've got to be, so there's something I was going to skip. And now to actually say why this is true, I can't quite skip it. So I think I'll close. This is actually a good point to close on, so I will make this point and then I'll close there. So amounts to studying action of SP2G Z mod LZ, the monodromy group, on the surjections from Z mod LZ to the 2G to Z mod LZ to the R. Or maybe dually on the injections from Z mod LZ to the R to Z mod LZ to the 2G. So let me make a comment here. So we saw that when R is 1, this is the injections from Z mod LZ to Z mod LZ to the 2G are the non-zero vectors, and we indeed know that the symplectic group acts transitively. But now you should complain, because when R is bigger than 1, now you think I'm going to say, oh, so this action is transitive, so the average is 1 again, just as Cohen-Lentzer predicts. Which is all great, except that this action is totally not transitive. So this is a bit of a confusing point. And by the way, it's important to mention, while we're talking about people in the room, I think the first person to recognize that the function field analog of Cohen-Lentzer suggested that somehow these guys should conform to random matrix predictions was Larry Washington. In a paper that was like very shortly after, right? Like 2 years after Cohen-Lentzer. The Friedman-Washington paper. And then there was actually this very interesting discussion in your paper about like, well, you do a thing for GLN, but like somehow really it should be symplectic, and there's like a bit of mystery about sort of why it agrees. So I don't quite have time to tell this whole story here, but so let me make the following couple of comments. But this action is not transitive, e.g., given an injection phi from z mod lz squared to z mod lz to the 2g, the pullback of the symplectic form to z mod lz squared is an invariant. I mean, that's not going to change when I hit with a symplectic matrix. So there's not so many symplectic forms on a one-dimensional space. It has to be 0 because it's alternating. So then there's really only one orbit. But once the space is of dimension bigger than 1, all hell breaks loose, and you actually have quite a lot of orbits. So what's going on? What's going on is that, and again, in my notes, I sort of write this up more carefully with the arithmetic fundamental group and the exact sequence between the arithmetic fundamental group and geometric fundamental group. I'm not going to do that here. Let me just say that, so what's going on, which is that really we are thinking not about sp2gzl. I mean, because really in the end, we're asking about the Frobenius fixed points. We're doing some kind of Burnside theorem argument where the average number of Frobenius fixed points has to do with the orbits of Frobenius acting on something. But Frobenius does not act symplectically on the L torsion. It acts generalized symplectically. I mean, moving around in the space geometrically preserves the Weil pairing, but Frobenius does not preserve the Weil pairing. It multiplies it by Q, and this is critical. So but what you might call, it's a certain coset of sp2g inside gsp2g, namely the coset of guys which multiply the symplectic form by Q. And then there's again, it's sort of it's all in the notes, but there's sort of a fun Burnside game you can play where when you compute the average number of fixed points of something drawn from this coset, what you find is that the relevant quantity is actually, so it turns out, so remember, what we're supposed to be counting is irreducible components of the space which are defined over FQ. So this non-transitivity shows you that there are lots of irreducible components. So thus, lots of irreducible components. It's not connected like it was for Challa. So then you're like, well, then maybe the average should be much bigger. But no, because Frobenius acts on those components, and amazingly enough, only one of them is fixed. So you get the one again. So let me say how this works. So it turns out that the action of Frob on these components is to multiply this invariant, the pullback of the symplectic form, by Q. And you're looking for those which are fixed by Frobenius. But now you have a quadratic form, or a symplectic form, which is fixed when you multiply it by Q. So that means it's killed by multiplication by Q minus 1. So then you say, so it must be 0. So the only fixed ones is when the pullback of the form is 0, i.e. the orbit of isotropic subspaces in Z mod LZ to the 2G, and indeed the symplectic group does act transitively on those, or at least on the, and that's it's sort of like the symplectic Witt theorem. And so there you get 1. So this is sort of a sketch of the proof that, that in the sort of large Q regime, those Cohen-Lenstra averages really are all 1. let me say two things. One, I'm not going to actually tell you anything because I'm out of time about what we actually know about the fixed Q case, but this is the subject of my paper with actually Venkatesh and Craig Westerlund. So I'll just say we do know something. We know even without letting Q go to infinity, we know that that limit exists. At the moment, we don't know that it equals 1. But I want to say one more thing, because one sort of somehow aspect of the problem that I have not really emphasized in these talks is that this geometric business is not just for studying function field versions of conjectures we already have. It's also sort of a machine for generating new conjectures. So let me now say something I just said that was wrong. I said the only one that's fixed by multiplication by Q is 0. That's true unless Q is 1. I mean, being fixed by multiplication by 1 is easy. So unless Q is 1. And of course, I mean Q is 1 mod L, because we're in a mod L situation. In which case, all orbits are fixed. And the Cohen-Lenstra distribution is just replaced by something else. Somehow the Cohen-Lenstra averages that I wrote down, the conjecture just should not be right in that case. So what am I saying? Am I saying Cohen-Lenstra is right, or am I saying Cohen-Lenstra is wrong? Well, let's think about what I'm saying. I'm saying that, let's for instance think about the case of L equals 3. I'm saying if Q is 2 mod 3, then I claim that this geometric argument is sort of ratifying the original, the Cohen-Lenstra conjecture that we know. But if Q is 1 mod 3, somehow these averages are bigger. There's more rational orbits and the averages come out bigger. But we think Cohen-Lenstra is true. So what's going on? Well, what's going on is that to say that Q is 1 mod 3 is to say that your field contains the cube root of unity. That's the sort of number fieldy way of describing that condition. Does Q have a cube root of unity? No, it does not. And so that's why somehow you should think of, I mean, if you were to think of Q as a function field, you should think of it as one where Q is negative, never 1 mod anything except 2, because it doesn't have any roots of unity besides zeta 2. And what's interesting is, like, sort of as the story was being worked out, something else was happening, which is the people were investigating these with modern computational tools, these generalized Cohen-Lenstra conjectures or Cohen-Lenstra-Martinet conjectures over larger number fields. And what Günther Mahler discovered is that there was cases where you tried to do Cohen-Lenstra for the 3 part of the class group of quadratic extensions of a number field, and it seemed totally out of whack. What number field? Q adjoined zeta 3. And he wrote a paper saying, like, you know, what's going on? Like, Cohen-Lenstra is sort of somehow clearly wrong in this case. The average is okay. The first moment agrees, but the second moment is totally off. And what's going on is exactly this. So I'll just say, if you look at, I mean, the thesis of my student Derek Garton is precisely about this. See work of Garton, and what's cool, I mean, is that you can look at what's supposed to happen when Q is 1 mod L, and you can sort of in this geometrically principled way generate a modified version of the conjecture which exactly corresponds with what Mahler got, and then it gets more and more complicated, but you can even sort of do the L-atic version. Then it depends on, in some way that is still being worked out, it's quite combinatorially complicated, on exactly what power of L divides Q minus 1. So the conclusion is just that this is supposed to be not only a way to hopefully get evidence for conjectures we already have, but I hope to kind of clarify what we expect to be the conjectural picture in situations in the number field case where we have not yet made conjectures. So I'll stop there. Thanks very much for coming to my course.